Yet dark matter is only known to us through its gravitational pull on ordinary matter. Here, clouds of gas are blue and stars are yellow. The dark matter is unseen, but its gravity helps the gas to clump together and form a galaxy.
Hi, here we are with In the Loop Art and Technology, and I have some very special guests, Nancy Abrams and Joel Primack. Joel Primack, as a lot of people know in Santa Cruz, is a professor at UCSC, and you two together had a class called Cosmology and Culture.
Right.
And because of that, you did your first book, View from the Center of the Universe. Joel, you are also in charge of the NASA supercomputers simulating the evolution of the universe. I know you've been on other specials, like a National Geographic special.
Yes.
Inside the Milky Way. Then Nancy Abrams, you are a lawyer, a writer, Fulbright scholar, and musician, and more of a music video producer these days. And you were on the staff of the U.S. Congress concerning scientific uncertainty. And anything you've been doing in the last year that is of major importance?
Well, I'll mention that I'm the director of a new University of California system-wide institute called the High Performance Astrocomputing Center. So it's located at UC Santa Cruz, but it's actually for the entire University of California system. I'm also currently the chair of the Computer and Communications Committee of the entire University of California. You mentioned that my group uses NASA's big supercomputers. We're one of their biggest users. Their supercomputers are all at NASA Ames Research Center in Mountain View. And we've done the biggest and best simulation so far of the structure and evolution of the entire universe. We do a big piece of the universe, about 1 billion light years across, and we show how that evolved, starting from the Big Bang. We've also run sort of smaller simulations for public consumption. For example, the most advanced planetarium in the world is the Adler Planetarium in Chicago. It's the oldest and biggest in the United States, but they've just souped it up, put in all new equipment, 20 projectors that can fill this big dome with 8,000 pixels across. So it's basically IMAX in a dome, and they wanted to have a spectacular opening for their first show, so my group did that for them.
With your simulations of the evolution of the universe, were there any surprises that you found?
The first thing to say is that the agreement between our simulation and the actual observations of the universe is spectacularly good. We were hoping it would be, but until you actually run the sort of thing and then compare it to the real universe, you never know. So we can predict how the galaxies are distributed. They're on long filaments, and where the filaments cross, they're clusters of galaxies. And so we can predict the properties of the galaxies, how close they are to each other, how they're distributed, and we can check that against the real data, and it's bang on. So what we're looking at is a region about 200 million light years across, which is actually just a small part of our really big simulation that we call Bolshoi, which is Russian for big. And each one of these little blobs would represent probably one or at most a couple of Milky Way-sized galaxies. Basically, all the structure is forming along these filaments of dark matter. And also, if you look in the early universe, before the universe had evolved to its current state, we made different predictions for that. Those also seem just fine. We can even predict how the galaxies have satellites. So our Milky Way galaxy has 2 bright satellite galaxies that you can see easily with the naked eye in the southern hemisphere. So they were discovered on the voyage of Magellan and his ships going around the world for the first time. And they went below the equator, and they saw these things, and they're called the Magellanic Clouds. Well, the Milky Way has 2 bright satellites, these 2 Magellanic Clouds. So how often does that occur? Well, we can ask the simulation, because we have, you know, hundreds, thousands of Milky Way galaxies in our simulation. And the answer is about 5% of the time. Mostly, we're going to have a galaxy as bright as the Milky Way with no such bright satellites. And about 20% of the time, it'll have one such bright satellite. But it's pretty rare that it'll have two. And then we can actually look at the big survey of the sky that's ongoing called the Sloan Digital Sky Survey. And we can check how many have no such bright satellite, how many have one, how many have two, how many have three. It's exactly as the theory predicted. So that part has worked out just great. On the other hand, the number of really faint galaxies, not satellites, but in between the other galaxies, is higher than we actually see. And is that a problem? Or is it just that our telescopes aren't yet powerful enough, or they haven't been used properly to see the really faint galaxies out some distance away? That's an interesting question that we're going to find out much more about in the next year or two. Because now that we've published our results, people are out looking to see if that's a problem, or maybe just they didn't look hard enough.
And should I say that you are the person that founded dark matter, dark energy, or are you part of a team?
Well, the first article that proposed the modern theory, the theory that we now all basically think is right, was a paper published in 1984 by George Blumenthal, who's now the chancellor of UCSC, Sandra Faber, one of the most prominent observational astronomers in the entire world, recently the chair of the University of California at Santa Cruz Astronomy Department, and the leader of 3 big projects in astronomy right now, me, and Martin Rees. Martin just retired as the president of the Royal Society of England. He is still the Astronomer Royal of England, and in honor of his service at the highest levels, he is now Lord Rees. Our paper basically established the cold dark matter theory, which is the modern theory of how the universe works, what it's made of, how it evolved. And I'm the one who actually wrote the paper. I mean, the other people, each of us, I think, had a major contribution, but the idea of putting it all together was mine.
Okay.
So yes, I had something to do with that. And of course, I've continued to be one of the leaders in developing these ideas.
You are not only just a scientist, but together you two are cosmologists. So what is the difference between, what is cosmology? What is that statement?
Well, I'm not a cosmologist. I really am an artist. I mean, I'm a writer and I'm a musician, and it's true that I'm a lawyer, but that doesn't enter too much into what I'm doing right here. The important thing is what we're trying to do is we're trying to present this modern picture of the universe that Joel was in at the beginning, and he's been working on it all along. We're trying to present this in such a way that people can actually visualize the invisible, and they have to, because every single thing that we can see in the universe, all the distant galaxies, all the stars, the dust, the gas, everything we can see with all of our instruments is really only 0.5% of what's out there. So there's no way to really get some kind of a sense of what's out there, the 99.5%, unless we can figure out how to visualize it, even though it's actually invisible. So Joel does his simulations, and then he turns them into movies. And we also try through words. This is really what I try to do. I try to give people a feel of what it means that all this stuff is out there that we have never seen and no one even imagined until very recent times. Mm-hmm. So that is an art, really, even just describing it. And one of the things I do in The View from the Center of the Universe is what I call contemplations. This is something that I started doing in our class at UCSC when it was really hard for the students to, I guess, to believe what we were telling them. So they're kind of guided meditations that help you to imagine what it would be like if you really believed what we were teaching you. And it takes the students out of their sort of analytic brain and just puts them into the feeling of this is reality. So they worked in our class in a very interesting way, and so we put a few of those into that book.
Well, I think one of the things that I really got out of the book too was your beginning of your history of how important cosmology is, how important it is to us to understand where we are in the universe, and the fact that the cosmologies of the past put us at the center of the universe.
Every mythology, and there have been countless mythologies, every culture has had one, the people were always the center, and that's how they saw the world around them. And for example, in ancient Egypt even, not only were they central, but they thought that the people, what we would call people, weren't really people because they weren't part of Egypt. And Egypt was what the gods had created. They really had this completely Egypt-centric view. So this is actually pretty typical. And people have seen themselves as central to the universe all the way up through the Middle Ages, when at that point they believed the Earth was the center of the universe and everything revolved around the Earth every day. And then in the Copernican revolution, which is, Copernicus, Galileo, Kepler, and Newton, I guess you'd put it up to, you could ascribe it to them. At the end of that period, they had basically shown that the Earth is not the center of the universe, that it's a planet, and it moves, and it goes around the sun, and the sun is also possibly not the center of the universe. So for the few hundred years since then, Western culture has pretty much believed that we live on an average planet of an average star in a universe where no place is central, no place is special. And that is really, although on a small scale, it's true, if you just look at our local region, it's psychologically a weird place to be, and no culture ever has had to deal with that. And it's sort of pushed us out of our own center. So what Joel and I have been able to do, which we did not intend to do, this was a discovery for us. We did not plan to put ourselves back at the center of the universe. But as we were trying to teach the fundamental principles of this modern picture of cosmology, we realized that we, not the whole Earth, but intelligent life, actually is central, not physically, not geographically central to the universe, because there is, in fact, no middle point to an expanding universe. But we turn out to be central to the principles that underlie this modern picture. And once we started realizing that we could see ourselves that way, we started discovering more and more ways that were central. By the time we wrote that book, we had 7, I think, and now we've got 8. We have a new book that just came out this year, and we have a new way in which we've discovered that we're central. So it's not just humans. In some ways that are pertaining to Earth, of course, it's just humans, but intelligent life is actually central in very deep and interesting ways.
And one of the descriptions is how you describe how rare we are, how rare the substance we're made of is. So that puts us at a center point.
Well, we are made of stardust. And stardust is, what is it, 0.01, what's the percent of the universe. So what stardust is it's the heavy atoms that get blown out of stars when they supernova. Sometimes the atoms were created inside the stars earlier, sometimes they're created right at the supernova. But the point is that a star, most of a star is just hydrogen and helium. But it creates these heavy things like carbon and oxygen and nitrogen and iron inside stars. And then when they blow out, those atoms just get blown throughout the universe and they just float around. They can float for eons. And then they can get picked up in the gravitational field of a newly forming solar system, and that's what happened here. And we, not just our bodies, our whole planet, is made of this incredibly rare substance.
I'll just read one little quote here. I read this before on my show. I just love this. This is from The View of the Center of the Universe. And it says, the history of the universe is in every one of us. Every particle in our bodies has a multi-billion-year past. Each of us is a kind of nerve center where these various cosmic histories intersect, which in a little bit of a way, I think, talks into your new book, The New Universe and the Human Future. And that's come out this year?
Yes.
I want to talk about your new book?
One of the things that we point out is that the Industrial Revolution was a transformation of the way humans relate to the Earth. Up until the Industrial Revolution, people could have a fairly important local impact on the environment. They could cut down trees or burn fires that kept trees from growing back and create plains. But they didn't change the whole world. But starting with the Industrial Revolution, we've been able to produce machines and great factories and things like that that can have a huge impact. Not right away, but as things developed. The speed can be characterized by a doubling time. The length of time it takes the, for example, amount of resources that we use to double. And it's been about 30 years. So every 30 years, starting about 1800, we humans have used about twice as much coal and oil and things like that, and about twice as much iron ore, and about twice as much lots of other stuff. And after a few of these doublings, the impacts began to be seen. London became one of the smoggiest cities in the world. Manchester had been earlier. People cleaned up some of the local problems. But now we're having an impact on the entire world. The amount of carbon dioxide in the atmosphere was between 200 and 300 parts per million during at least the last million years or so, and probably a lot longer than that. During the ice ages, it would go down. During the warm periods, it would come up, but it was always in that range. It's now about 400 parts per million. So it's much higher than it's been for a long time, but it's shooting up. It's the amount that we're putting out is what's responsible, and that's doubling every 30 years. If it doubles again, then we're going to be up to about twice the amount that was in the atmosphere for the last million years or so. And the consequence is that the climate is going to change in ways we're not completely sure of, but it'll certainly get hotter on average. If there's yet another doubling, then we're going to be up at catastrophic levels where the Earth will be hotter than it's been for an awfully long time. One of the things this means is that all of the local flora is going to die. Trees in particular, because forests can't move. Animals can move, and they are moving. They're moving poleward. But the forests can't move. And for example, our wonderful local redwoods aren't going to be here. There won't be any redwoods south of Marin County.
Not living ones.
Right. So, and this is going to happen on a very short time scale. We're talking about 30 years and then another 30 years. We've got to bring this under control. So that's what's so special about this particular moment, that we've reached the end of this doubling every so many years, this exponential expansion. Mm-hmm. We can't keep doing it. The Earth is going to prevent us, or we can be smart. In the book, we talk about a hypothetical bloom of pond scum that doubles every day. For the first several days, the pond looks clear. You could hardly notice it. In fact, you don't really see much change until the pond is nearly finished being filled with pond scum, because it doubles and then doubles, and when it's just about finished, it's only half doubled the day before, and only a quarter the day before that. As soon as you can even notice it, you're really in danger. And then the whole pond could just die. Everything in it gets choked off. Well, things like that actually happen in nature. You get these algal blooms off the coast, for example, where you kill a lot of sea organisms and so forth. That could happen to us. Or maybe we're smarter than pond scum.
Let me make the connection to cosmology here, because now these are problems on Earth that a lot of people are aware of, especially here in Santa Cruz, which is one of the most progressive places in America, and I think probably the most conscious. So people know about the problem, but the question is, how can we change our way of thinking so that we can actually start dealing with it in a positive and optimistic way? And we need a bigger context. We need to understand how to think about time in the long term. And one of the things you really learn from cosmology is there has been 13.7 billion years. It took almost that long to create us. We are really newcomers. We humans are really newcomers on the scene. I mean, suppose we've been here 1 million years out of 13.7 billion. It took all those years to create us. We are really one of the masterpieces of the universe. And I'm fine saying that. I mean, there may be many alien worlds out there with intelligent aliens, but all of us intelligent, the aliens and us together, are still a tiny, 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 tiny fraction of this universe. We are incredibly rare, and we are valuable because we are the only way the universe can think about itself, can start to understand itself, reflect on itself, care about itself, appreciate itself. We are the thinking part of the universe. We matter. We really can't wipe ourselves out. And the fact is, we don't know if there's any other aliens. So it could very well, we could be the first.
Well, one of your main lines in the book is, think cosmically, act globally.
Think cosmically, act globally, exactly.
Eat locally.
Eat locally.
Sometimes we have a bumper sticker, we had the eat locally part of it. But think cosmically, act globally is really, that really is the lesson of that first book. Because what we're trying to say is that we need a context. We need to understand that it's not as though we can just write ourselves off. I mean, a lot of people, a lot of environmentalists are actually out there saying, well, Earth would be better off without us because we're messing it up. That is such a short-sighted view. First of all, Earth wouldn't know it was better off without us because there'd be nobody to know that. If all the animals were here and we were not, nobody would be here appreciating that we were not here. That's one thing. And the other thing is, Earth may really have to put up with us because we are an amazing experiment of the whole universe. And we have to start somewhere. We have to learn how to live. The most important thing is to figure out how we can have a long time to learn how to live properly. And the only way to do that is to live sustainably, to figure out a sustainable relationship between humans and the Earth. And I think that cosmology can not only give us a long time scale, but it can give us a shared picture of reality, the first one in centuries that's actually based on science.
And
let me give one example from cosmology that relates to that story I was telling about this exponential growth, this extremely rapid growth in our use of resources and our production of things like carbon dioxide. The early universe, right at the earliest moment of the Big Bang, or if you like, just before the Big Bang, to get the Big Bang started, underwent a process where any little region doubled in size, and then doubled in size again, and then doubled in size again, just like the human resource consumption. And this kept going on for at least 100 doublings. And then at the end of that, the universe stopped growing so fast and grew fairly rapidly, but at a rate that was actually much, much slower. And then it kept slowing down, in fact, until about 5 billion years ago, when it turns out it started speeding up again. That's a different story. But this part at the beginning, there really was this exponential growth, this doubling every so much time, doubling, 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 just like we've been doing since the Industrial Revolution began. When that was over, the blueprint had been laid down because of tiny quantum fluctuations that got blown up by this tremendous expansion. For all the large structures in the universe, all the galaxies were determined where they were going to be. All the clusters of galaxies and superclusters, it was all laid down in those earliest moments. And then gravity basically did its work, and all these different parts of the universe work together to make the structures we see today. That's our modern picture, which, as I said, really agrees beautifully with the observations. So we're pretty sure it's right. Now, the human situation is going to be quite similar. the things that we're doing, the species that we're killing or not killing, we're killing species at a faster rate than probably since the extinction of the dinosaurs 65 million years ago. The things that we're doing on the Earth, and nearby even, are going to determine the future for a very long time.
That blueprint.
That blueprint.
So even little tiny things we do now can affect that blueprint coming up.
And the thing that's really kind of worrisome is who's thinking about that? Who's thinking even 5 years or 50 years in advance? The impact, the carbon dioxide we're putting out now is going to change the sea level for at least 1,000 years, probably thousands. Who's thinking on those kinds of timescales? Certainly not the politicians.
So that's why we need to start thinking cosmically,
Exactly.
at least on those kind of time scales. Because as you said right here, we're the beginning of a new kind of a universe just by our existence, the universe that reflects on itself. So the little tiny things we do now are going to create those patterns, such as
Right.
your filaments of galaxies. So it's an interesting model for reflecting on itself.
Well, and another point. So during this extremely rapid expansion in the early universe, the blueprint was laid down for the large-scale structure of the universe. But all the really exciting things that made the universe so interesting happened later. The early universe had no heavy elements at all. It was just hydrogen and helium. All the heavy elements were created as galaxies formed, and then stars formed within the galaxies, and generations of stars formed. Stars would explode or end their lives in other ways, and the stardust would come out, and then after a while there was enough stardust to start making planets. And on certain planets the conditions were favorable and life came into existence, and then life got more and more and more complicated. But on Earth life was just single-celled creatures for almost 4 billion years. And it's only in the last about 500 million years that all the complicated kinds of life developed. So all of those interesting things happened, and finally we came along, after the universe stopped expanding exponentially. So during these very long periods of not such tremendous transformation on the grand scale, but wonderful complexity development on the small scale, that's what made the universe so interesting. We can have a very interesting future. Our galaxy is going to continue for 1 trillion years at least. In fact, it's going to be brighter 1 trillion years from now. The stars in our galaxy will continually get brighter. Some of them will burn out, but the little ones will get brighter and brighter. So 1 trillion years from now, our galaxy will be brighter than it is now.
And
1 trillion years is 1,000 billion years.
And we could, if we're still around, assuming, we could still see that? Are they
Absolutely.
not going away from us?
No.
Okay.
So what's happening is that all the parts of the universe that are held together by gravity, our galaxy and all the nearby galaxies are actually held together by gravity. That's not expanding. In fact, it's contracting. Our galaxy is headed toward the nearest big galaxy, and it's headed toward us. It's the great galaxy in Andromeda. You can see it with the naked eye if you know where to look. If you can see the Milky Way in the northern hemisphere, you can see Andromeda. You just have to know where to look. And that galaxy's now far away from us, about 2 million light years away. But the two galaxies are coming together at a high rate of speed, and in about 3 billion years, they're going to be close enough to start feeling the effects of each other. And ultimately, in about 5 billion years, they're going to have joined together to make a new galaxy. We could call it Milky Andromeda. And the other nearby galaxies will join together. The distant galaxies, the ones that are tens of millions of light years away, they are moving away from us. And they're going to move away from us faster and faster. So the most distant galaxies are already starting to disappear. And more galaxies will disappear. And when the universe is twice its present age, none of the really distant galaxies will be visible. And the sky will be much less interesting than this wonderful sky we can see with Hubble Space Telescope.
Well, you have seen to the edge of the universe. You have seen to the beginning of time.
Yes. And the cover of the New Universe and the Human Future, the inside of the outermost dome shows the heat radiation of the Big Bang. That's radiation that was
Well,
emitted.
let me just say what this is, though. This is our picture of the universe from the point of view of time. It is what we call the cosmic spheres of time. And what we did was we took the medieval understanding of the universe, which was that Earth is at the center, and each of the planets had its own little sphere and moved around the Earth, and then all the stars were on one sphere, the outermost sphere, and they all the whole sphere just rotated around the Earth every day. So we took that because although it was wrong astronomically, it was right psychologically. People really do feel like the center. They look out, I mean, obviously everything is around us. So when we look out into the universe, because light travels at a finite speed, when we look out into the universe, we're actually looking back in time. So that the farther away an object is that we're seeing, the earlier we're seeing it in the history of the universe. So we can see the very, very distant galaxies when they were extremely young. So what this picture shows is spheres that represent not just space, but time. Each sphere represents an earlier and earlier epoch in the history of the universe. So that when you look out into the more distant spheres, you see galaxies that don't look like modern galaxies. They look like very rough, messy galaxies, the way the galaxies look when they're just getting started.
Okay.
Yeah, those that you're pointing at.
Right there.
Yeah.
Yeah, exactly.
And then you look into the next sphere, the really big one, it's empty because galaxies hadn't formed yet. You're really looking back earlier than galaxies has formed. And then that colorful sphere is the cosmic microwave background radiation. That's the leftover heat from the Big Bang, from the explosion of the Big Bang. And that can be seen. And then the very outermost sphere is the Big Bang itself. So that's what that represents.
The different colors in that colorful outer sphere represent differences in temperature of only a few millionths of a degree.
Okay.
But we're carefully measuring that with a satellite that NASA put up around 2000 called the Wilkinson Microwave Anisotropy Probe, WMAP for short. The Europeans have put up a more advanced satellite called Planck, and in a year or so, they're going to reveal the map that Planck has made, and it'll be 10 times finer than our map.
Oh, interesting.
Because the equipment keeps getting better as time goes on.
Okay.
And of course, the Europeans want to compete with us and show we can do better than you.
And do you think they'll find other things other than temperature variations, and do you think
It's
there'll be
possible.
some more surprises?
So one of my colleagues in the physics department here at UCSC, Anthony Aguirre, Professor Aguirre, and his brilliant student, Matt Johnson, showed a couple of years ago that there's a chance that if we have fine enough measurements of the cosmic background radiation, we can see evidence of what might have happened before the Big Bang. So there's a complicated
That's
theory
scary.
of what might have happened before the Big Bang. It's called eternal inflation.
Okay.
And for quite some time, we thought it was just a fairy tale because, you know, it might have happened, it might not have happened, but there's no way to tell. But then Aguirre and Johnson showed maybe there's actually a way to tell by doing more careful studies. And so as soon as this data is revealed, it's being collected now.
We'll do another interview when that happens.
Yeah. So it's just possible that we may discover something truly amazing about what happened before the Big Bang.
If you think of combining science and religion, it sounds like you're getting to pretty much to that point where you think, will you find God? And I also know you had said that a lot of very religious people have really loved your book. So how does that blend together?
It is interesting. We've been invited to speak in churches and synagogues. The number of people who are interested in learning about the universe is really large, and many religious people are very open to this because religious people want to have some kind of a sense of how they're connected to the larger reality. And they use different metaphors to describe the larger reality. Every religion has its own set of metaphors. But there's a kind of an innate impulse to feel connected to something really important and big that you know you're a part of. I think everybody has this. And for some people, it's a religion. For some people, it's the scientific endeavor. I know for a lot of scientists, what they want to be connected is to the scientific endeavor itself. They want to be a part of it. They want to make a big contribution. But really, it's the same psychological impulse. So I think that we're really able to say something to people about what the universe is like. And to those people who believe that God created the universe, they're interested in, what is it? What is the universe? I have my own views on that, but that's another matter.
Well, it seems too, you're also, especially with the need for cosmology, for the sociology of how we live, that you are combining religion and sociology, in anthropology, into real science. And it's really science that is going to, in some way, affect how our religious thinking is.
I think religion isn't quite the right word. We never talk about religion. But we do talk about a spiritual connection to the universe. And in a very interesting way, you can think of the part of the universe that is completely beyond all human experience, that is the very, very smallest size scales, the atomic size scale, the subatomic size scale, and so forth, and the very large size scales, the size scales that Joel's visualizations are showing. So we can think of these incredibly large size scales and the incredibly small size scales, which we humans can't possibly directly connect to. We can think of those as spiritual realms, because we really do only connect to them through the spirit, through the intellect, through science. But they're real. But they're real, and they're absolutely governed by
them.
We are part of them, and we are only here because they're here. They are our source.
Mm. And maybe in some way, I can't say we feel that, but there's some innate understanding. I mean, when people say, "Oh, God is in us," I mean, you're kind of saying the same thing. We are part of that universal process of the expansion. I mean, it kind of all is its own.
Yeah, I think the more people actually do feel, in some kind of emotional way, the big picture, and also the small picture, they actually can have an emotional attachment to the universe that I think deepens all of our experiences. So I don't think that this is beyond what people can do. They just need to know a little bit more and then really think about it. And these thoughts that we've already mentioned, that section that you read, that we are made of the stuff that came out of the Big Bang. And a lot of that stuff wouldn't be interesting except that it's been in stars. And it was transformed in stars into more complicated elements. The human body is made mostly of oxygen. Something like 80% of my mass and yours is oxygen. And hydrogen, it's only about 10% hydrogen, but there's a lot of hydrogen atoms. And carbon and nitrogen, those are the four elements that are the most common ones that we're made of. Except for the hydrogen, they were all made in stars. The hydrogen is right out of the Big Bang. And then there's a little bit of heavy stuff like iron, also made in stars. So each of us represents this evolution of the universe and then this complicated evolution on Earth. And the more we understand where we came from, the more of our history we can claim.
And the more miraculous it feels.
And the more we're connected to the past, we could be connected to the future.
And the more we feel committed to the future.
Well, on a small time scale, being that this is the beginning of the year 2012, I mean, in mythology, we think that this may be the end of something, but really it's the beginning of something. So why is 2012 suddenly an issue?
Well, so what happened was that there is this Mayan monument. It's called Monument 6. And it is about 80 lines. And the last 8 of them, only the last 8 of them, deal with the future. So some people here in the West completely misinterpreted this. They really did not understand the glyphs. And they somehow thought that this said that the world was going to end in 2012. In fact, the Mayans had time periods, like we have decades and centuries. They had 20-year periods and 400-year periods. There's cycles. And all of this is based, all of this stuff has been misinterpreted from a line that said that at the end of the 400-year cycle, which is 2012, the patron deity of the ends of cycles will return to help us celebrate and do the ceremonies for the end of the cycle and the beginning of the new cycle. There's nothing about the end of the universe. There's nothing even about the end of the calendar. Other glyphs say that something happens in the year 4772. So obviously they did not intend that the world was going to end in 2012. So it's very unfortunate that this has become such a big deal because, I mean, a lot of us here in the United States think this is just fun and games, but apparently it's had a very negative effect on many people in Latin America who, because they have Mayan blood, feel they ought to be able to understand this, and they've been affected by what's going on in the Northern Hemisphere, especially that movie, I suppose. And it's had bad effects. I just feel bad that people are taking this so seriously when it's really...
Actually, let me tell you a little story about another group of Maya. They're called the Highland Maya. I think another name is the Chamula. And there was a professor here at UCSC, Gary Gossens, who was a big expert. He's published books about them. Here's what he learned from the Highland Maya. They thought that they were the most advanced people in the world, and that the people who lived far away were people, but they were more primitive. And the people who lived still farther away, well, they hadn't actually seen any people like that, but they thought, extrapolating, they must be even more primitive.
And so they thought they were the center of the universe too.
Yes.
But exactly the same way that we really are, in the sense that as we look out, we look back in time.
On a different sense.
The pictures that we get in our telescopes of distant galaxies are pictures that we see because the light left longer and longer ago to get here now. And so it's exactly as the Maya were thinking, except they weren't thinking cosmologically, of course.
Funny.
But they actually had the right picture. That's, for a cosmologist, that's really neat. But anyway, they had funny ideas about time. And that's another idea that's really documented. That's clearly the way they, at least this group of Maya, thought. Maybe they still think that way. So it gives you a little bit more perspective when you hear about other people's views of time and centuries and so forth.
And then on the other myth of some kind that seems to be coming up for the year 2012 is this galactic or Earth wobble. Every 26,000 years there's going to be a new cycle and we're coming to the end of it. I mean, okay, now debunk that theory too.
Well, so the Earth is a big top. It spins around its axis once every day, of course, and just as a top sitting on a table, because of an interaction between the angular momentum of the top and the gravity that's pulling it down, the top wobbles slowly. The technical term is precession. Well, the Earth's axis precesses, and it takes about 26,000 years to go all the way around. So the axis of the Earth currently points in the direction of a certain star that we call the North Star, or Polaris. But 2,000 years ago, the axis of the Earth didn't actually point to any decently bright star at all. There was no North Star. Shakespeare, in his play Julius Caesar, has Julius Caesar say that he's as constant as the North Star. Well, Shakespeare apparently didn't know much about astronomy, but Greek astronomers figured out 200 years BC that this process occurs, that the axis of the Earth doesn't stay fixed. There's nothing special that happens at any particular year. It's a continuous process. It just keeps precessing around. But of course, the Babylonians and other ancient civilizations divided the sky up into certain constellations. So maybe because it takes Jupiter 12 years to go around the sun, the Babylonians divided it up into 12 constellations, which we call the zodiac. And so what happens is that the sun at a certain time of the year is in one constellation, but at that same time, thousands of years ago, it was in a different constellation. So people who studied astrology know that the astrological signs are out of sync. And the reason they're out of sync is that they were set up more than 2,000 years ago, but the precession of the Earth has caused the seasons to change so that the sun isn't in the same house, as the astrologists would say, that it was 2,000 years ago. So there's, in fact, different schools of astrology where they correct for this or they don't correct for this.
So I'm not really a Pisces.
I
I'm
mean,
an Aries.
Right. So see, what that meant was that the sun was in that direction when you were born.
Okay.
But in fact, if you use the standard Babylonian astrology, it wasn't. They're all off by at least a month.
Okay.
So is this of deep significance? Well, no. You know, these astrological symbols, these constellations, are more or less arbitrary groupings of stars.
But again, it's us looking for some kind of constant cosmology to. And what's interesting, though, is they did look at that time to something somewhat scientific. It was just the lens that they interpreted it in was.
Well, the night sky.
Well, they didn't understand what was going on. You know, the Babylonians, they certainly paid a lot of attention. They observed. They kept records of their observations for centuries. They could predict eclipses and so forth. But they didn't have a model in their mind of what was going on. They just saw things moving across the sky. They had no idea that they were a sphere and what was going on. Although the Greeks figured that out.
In that light, for the year 2012, how should we think of it? How should we think of this? What can we do, for instance, to make...
We can elect people who are going to save the world. That's the most important thing we can possibly do in the year 2012. You know, we brought this up a little bit earlier, and the gist of this book, The New Universe and the Human Future, is the connection between a long-term view that you can get from cosmology and looking at what is going on in our world today and what are going to be the long-term consequences that nobody is paying any attention to. So, I mean, there's just so much horse trading going on and compromises on things that are going to have long-term effects, while the compromise is made for some very short-term thing, like to get some other law passed that, okay, I'll vote for this if you vote for that, even though this could have consequences for 3,000 years, and this is just going to be a few bucks in somebody else's pocket. I mean, that kind of trading, where there's no understanding of the different scales of importance, is really terrifying. And it's one of the things that I think people really have to become aware of. And I hope that by seeing that we now have a picture of the universe, the very first picture of the universe, that might actually be true in all of human history, we have something that we can agree on. We really need to agree on something. We need to start with some kind of basic picture of reality. And also see that there are going to be extremely long-term consequences to things being discussed in Washington right now, maybe even this week.
Now, on a somewhat more humorous and human-centered scale, we also could celebrate the new year by making a model of the composition of the universe.
I think I have it
so
right here.
At the end of the View from the Center of the Universe, we describe what we call the Cosmic Sunday.
Cosmic dessert.
Oh, let me read it, because this is made.
Okay.
This is so New Year's Eve is the beginning of a new year, but it's also a great day to celebrate the universe, to celebrate the beginning of the universe.
Or New Year's Day.
New Year's Day, of course. So what we propose here is the cosmic dessert. And this dessert reflects the way the universe is made. So we're going to rebuild the universe. So the bottom of it is chocolate cake. That's going to be 70%. And that represents dark energy, which is 70% of the universe. On top of that, you put chocolate ice cream, which is 25% of the total volume.
I think you're getting the idea.
And
the
that
universe is all
represents-
dark, so we use dark chocolate ice cream.
Yeah,
Okay.
chocolate
Or chocolate
represents
cake.
invisible stuff. And so the dark matter is chocolate ice cream.
Sounds good so far, though.
And then we put on, to represent the invisible mixed atoms, or 4% atoms. We use chopped nuts with ground coffee to make them look a little
And
dark.
you said those are invisible.
Right,
They're
'cause they're
invisible,
dark.
but
Okay,
they're not
4%.
invisible in principle. They're just invisible in fact.
Because
Well,
they're
in
not
fact,
lit up. They're not stars, and they're not
There's
lit up by
nothing shining
stars.
on them.
Okay, okay.
Then the visible hydrogen and helium, what all of the stars are made of that we see in all the galaxies, we use that, for that we use whipped cream. Now, since that's only 0.5%, we put whipped cream around the bottom too, just as a decoration, because that's not enough whipped cream. And then stardust is represented by the tiniest pinch of cinnamon you can actually see on top of the whipped cream. And that is the 0.01% of the universe, which is made of stardust. And
Which
then
is-
on top of that,
Which is where we are.
Right.
we are made of stardust.
And
but
our whole
that's-
planet is stardust.
But that's all the stardust. That's not just intelligent life. Now, intelligent life gets its own little representative, and it's the cherry on top, which is completely off scale because it's way too big. But
And
still,
in proportion, the cake would be as big as the United States
you
compared
mean if the
to
cherry
that?
were to,
Well,
were to
not
scale,
quite that big, but maybe,
very big.
California.
maybe as big as a block. But we recommend making this in a pyramid.
It's very hard to do. We tried that. very, very
Well,
messy.
yeah, it's a little tricky to cut it.
I think easier than a circle.
Absolutely. Anyway, in our course, the last time we taught the course at UCSC, a group of students actually made the cake, and we took a video of it.
beautiful.
They
good.
assembled
You
it
have
in
a
front of the
video it.
class.
Oh, okay, good. You'll have to
So-
send it to me.
But anyway, though that's another way that people can celebrate. Now, talking about
creative.
videos,
Right.
our new book has something like
fact-
24 videos
Yeah,
that
in
are
fact,
actually
I-
associated with the book. And if you have the electronic edition of the book, for example,
I have right
on your
here.
iPad,
Okay, so I have my iPad, and here it is, iPad style, maybe reflecting here. And you could go through and at different points, actually, click on things. And
so there's a little symbol if there's a video.
Mm-hmm.
We're not actually connected to the internet here. There's no Wi-Fi. But if you're in a place where you're connected and you tap on one of the symbols, up will pop the video. The videos are all on our website, and you don't have to have the electronic edition of the book. In fact, you don't have to have the book at all. The videos are all there for anyone to enjoy. The website is just new-universe.org. new-universe.org.
okay, okay.
And then there's other videos that have been made since the book was published. So just
And they're
recently,
on your website?
they're connected.
Okay.
So on new-universe.org, we have connections to the videos that we made based on this huge new simulation that we've done with NASA's biggest computers of the
Great.
evolution of the universe.
Okay, and you'll probably continue updating? You said that
Sure. We've just
coming up-
recently updated again. So
Okay.
yeah, of course,
And
we're constantly working on trying to figure out how the universe works. And so we have lots more videos, lots more scientific projects
And
underway.
the European visualizations that will come out, will they be in the year 2012?
They've postponed it.
Okay.
They had earlier said that they would come out in 2012. It's now expected spring of 2013.
Oh, okay, okay, then they'll be on your site.
We'll, of
probably as
course,
well.
make connections as this becomes available. We're pretty sure that 2012 is going to be a very exciting year for science, for physics in particular. There's some pretty convincing evidence that came out a couple of days ago that at the European Center for Nuclear Research in Geneva, CERN it's called, they are seeing evidence of the particle that gives all the other particles mass. It's called the Higgs particle. And the evidence isn't convincing yet, but it's pretty convincing. However, we're going to have something like 10 times as much data next year. The machine is ramping up. And so if it is really right, what these two different experiments saw, exactly the same mass, we're going to have a definitive detection next year.
Okay.
We might also start to see the dark matter. The same machine, this big collider in Geneva, might actually start making the dark matter. There'll be rare processes, so we have to have the machine really ramped up, but that's the plan. Next year it's going to be colliding a lot more protons, and so we may start to see this process. If not, at the end of next year, they're going to shut the machine down and they're going to upgrade it. And probably starting in 2014, they're going to be colliding the particles with twice as much energy. And so if they weren't able to make it before, there's a good chance they'll be able to make it again. I had suggested with the late Heinz Pagels back in 1982 that the dark matter is connected with a new theory called supersymmetry. And we're hoping that after the Higgs particle, the machine will start showing us this new world of particles called supersymmetric particles, and that could be the dark matter. Or maybe not. We won't know until we know.
Sounds like the subject of a new book.
Well, and then another thing that's happening is that people are looking very carefully at the history of the universe to try to figure out what the nature of the dark energy is, the thing that's made the universe start expanding faster. And I have heard through the grapevine that there's going to be a significant report in January. So the people involved are very tight-lipped, but they say it's interesting. It probably isn't going to be definitive. It'll be like the Higgs boson announcement. But there are big projects underway. And so I think 2012 is already looking very interesting scientifically.
Great, okay. And on the art side of it, just very briefly here, you have a few things, I must say, that we helped with this
Absolutely,
video.
we couldn't have done it without you.
Thank you. So this is on your website. You can
Yes.
still get that. And this is a lecture, a NASA lecture on pretty much following your book with graphics and movies clips
Right.
as well. And then you also have a new music video that you just
I do.
put up.
I have a music video. It's called Hired Brain. And you can find it on our YouTube channel, which is The Cosmic Society, all one word, The Cosmic Society. What this song is about is satire about the scientists who are trying to hold back the solution of problems because they muddy the waters so that those who are making money off the status quo can continue making money as long as possible, while problems like global warming and new energy sources get pushed aside. So it's really important to know about these people, but the song is actually a lot of fun.
I can testify convincingly to anything you like, try me and see. It's the consulting game. I'm an expert witness of forensic fame. I've got half a dozen letters after my name, which is on 97 articles and even a book. I've got influential friends every place you look.
Thank you so much for coming and beginning CTV's 2012.
Well, thanks very much for having us. It's been
Thanks
fun.
for having
Okay.
us, Denise.
I'd like to thank CTV, Ron Powell, our director, Matilda Rand, Lynn Dunton, and David Gibson on camera, Karen Scott on character generator, and Paul Logan on sound.